Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 42, and we are starting chapter 12, and we're talking about something called dummy variables and in regression. And last time we talked about interaction, and then we talked about something called confounding. And confounding, again, is when the inclusion of a variable, say a control variable, the inclusion of it drastically changes the estimate of the slope of another variable when it's included versus when it's not included, even if that variable, that control variable, is not considered significant. So that would be a case of confounding. All right. So in this chapter 12, we're going to talk about something that's referred to as dummy variables or indicator variables. So we're going to talk about the different indicator variables and how we use these in regression to test things that have just one level or multiple levels of a variable. Okay? So we have an indicator variable or dummy variable. It takes on a finite number of numeric values. In other words, we can take a categorical or a nominal variable and represent it. So something like male and female, those are not numbers, so we would have to, and even here we have it, so we could say 1 if the subject is female, 0 if it's male. Okay? And here's another example. So if treatment A is given, we would give it a value of 1 and 0 otherwise. Okay? Now, we have some variables here that have more than 2 levels. So Z1 and Z2 have 3 levels. So in this case, residence, if the residence is in the western U.S., the central U.S., or the eastern U.S. And again, this one is Z2 says 0 if in western, 1 if it's in central, and here it was 1 in western and 0 in central. And then eastern is still -1. Okay. Well, in regression, Z1 and Z2 are not allowed. Okay. We can't have indicator variables that have more than 2 levels. But what we can do here is we could set up Z1 equals 1 if western, okay, 0 otherwise. And then we could set Z2 equals 1 if central and 0 otherwise. So if Z1 and Z2 are both 0, then we know they're from the eastern U.S. Okay? So we would only need these 2 indicator variables to handle these 3 cases that we have here. Okay? So again, it's not okay to use a dummy variable that has more than 2 values in regression. All right? And well, we'll talk about that in a minute. So we're going to use this following rule to avoid case where the parameters or coefficients cannot be estimated uniquely, and that is very important. Okay, we need to be able to estimate our parameters uniquely, or else if they have multiple possible values, then how do we know that we have the right value? We don't. And it says that we need to follow this rule to make sure that we avoid collinearity as well. Okay, which we didn't talk about much in chapter 14, but we did talk about a little bit when we talked about the code. All right, so it says if a nominal variable has k categories, then we need exactly k minus 1 dummy variables. And notice that that's exactly what happened up here. We had 3 distinct categories, and we need k minus 1, which is 2 dummy variables to cover all 3 cases. So it's always going to be k minus 1 dummy variables. And again, if we used k, then we would end up 1 with collinearity. In other words, we would have some high level, or we could have some high level of correlation between those indicator variables. And two, we wouldn't have uniquely determined coefficients because we're oversaturating the model, and an oversaturated model is bad. And so this is one of those things that we have to be very careful with, okay? So, all right, and this says that as long as we have the intercept in the model, okay, provided that we have the intercept in the model. If it does not contain an intercept, then we need all k indicator variables to cover the k categories. All right, so if we have an intercept, which is usually we do, if we have an intercept, we need k minus 1 dummy variables. If we do not have an intercept, then we would need k dummy variables. But it's very rare that we don't have an intercept in our model. Okay. So here's an example, and I believe I gave this up above. So they're calling it, instead of Z1, they called it Z1 star and Z2 star. Now we could also have Z1 prime, and this is the western. So again, we're saying 1 if western, and here we're saying 1 if in eastern. Okay, and so if both are 0, then they would be in the central. Okay, in this case, Z1 prime equals Z2 prime equals 0 means central US. Here, Z1 star equals Z2 star equals 0 means eastern US. So which one you choose to be 0, 0 case is usually the one that what we call the baseline that we don't care very much about. It's the one that we assume, such as with education, we put the baseline as high school education, okay? And so we might put, so then we would have 1, let's say if it's more than high school, for one dummy variable, and 0 if high school, and the other dummy variable would be 1 if less than high school, and 0 if high school, because the 0, 0 case there is the one that most Americans have, is that we have high school education. On average, most people have that. And so that is the least interesting case for us. We want to know differences from that, okay? So one recommended way of coding is to only use the values of 0 and 1, and I recommend that. Unfortunately, some computer programs will use 1 and -1. In fact, I believe that by default, SPSS uses a 1 and -1, but a 1 and -1 makes the interpretation much more difficult. So it's a lot easier to interpret these when you have 0s and 1s because it shows up and you know that that's the presence of that variable. If it doesn't show up, if it's close to 0, that's the absence of that variable or the other case. All right. So we have to be very careful with interpretation. All right. So now let's talk about comparing two straight line regression equations. In that previous chapter, in chapter 11, we talked about the age and systolic blood pressure example, and we checked to see if there was a significant difference in the slopes between males and females. And we came up with a 0.96 and a 0.95, and our test said that there was no statistical difference between these slopes. And so we said that these were, for all practical purposes, parallel. Okay? So now we need to consider three questions. So are the two slopes, or we have three questions that we can consider. I'm sorry, we don't need to consider. We may want to consider these three questions. The first is, are the two slopes the same or different? And this is regardless of whether the intercepts are different. Okay, so we may just be interested in, are the slopes the same or not? We may be interested in, are the intercepts the same or not, regardless of the different slopes. And then finally, are both the slopes and intercepts the same? If they are the same, we call them coincident. They're identical, okay? So let's look at some examples of what we're saying here. These are parallel lines with different intercepts, So you'll see where they cross the y-axis would be in different spots. Here they have the same y-intercept, but obviously different slopes. And in C, we have intersecting lines, so not only do they have different intercepts, but they have different slopes as well. And then finally, D, these are the coincident lines. There's two lines here, but they're identical, so one is plotted on top of the other. So this is what a coincident line is. Both the slopes and the intercepts are the same. Okay. And these are some important questions that we have that come up in many applications. Okay. So there are two methods of comparing two straight lines. The first method or approach is we're going to treat, not threat, but treat the male and female data separately, and we're going to fit two separate regression equations, and you'll see that they're listed here, and then we can conduct two sample t-tests. This is a bad method. So we're not going to consider this method. This actually is not regression. This is actually taking something that can be handled very easily and efficiently with regression, and throwing away the regression and going back to a very cumbersome two-sample t-test. Okay, so we won't consider that method. So method 2 is the more preferred method that everyone embraces, and that is that we're going to define that dummy variable, let's say z, and we're going to let it be 0 for male and 1 for female. And let me also point out that over years and years, there have been data on males, but not on females. Okay? So for many years, all the data, all the analysis was done on males, and the assumption was there was no difference between males and females. But that is not true. So the majority of the data that we had was for males. So we're interested in 1 being for female instead of 1 being for male. That is kind of the baseline that we have all the data for years and years. But we don't have the data for females. So we want to know if females react differently in medical situations than males. And the answer many times is yes. Okay? So that is the reason that for most cases we will code females as 1 and males as 0. Okay? So we're going to let n of m be the number of males and n of f be the number of females. And so we're going to have, it says the data will be in this form. Really, what the data is going to be, the 0 is something we assigned here. We assign these to males. And so we'd have an x value, x1. So the first number here, so the number 1 refers to the subject, the first subject. And this is the x value, and this is the y value, and for the males, okay? And then this would be subject 2 for the males. And so this would be keeping the males and female subjects separate, okay? And you'll notice that the value for females would be a 1, okay? Now, I'm not really sure what data the authors are thinking about, but I never see data really in this format. I see so this would be z, I guess. So yes, so if this is a z value, yes, then we would have zeros and we would have 1s. But again, this is a unique, not unique, but this is a specific way of looking at this data, and not every data set looks like this. I just want to warn you that this is a fine way to do it, but it's not what every data set looks like. Most of the time, we're not denoting the difference between, we're not keeping tally of male number 1, female number 1, male number 2, female number 2. Not in many data sets. In some data sets, yes. And so apparently in the area of expertise of the authors, they do. Okay. So the combined data with a single multiple regression model would look like this. Okay. So, and you'll notice that we have beta naught, beta 1x, beta 2z, and then beta 3 x times z. So this is the interaction term. Okay. And when we have z equals 0, notice that when we have z equals 0, any term that has z in it disappears. So this term and this term disappears, and we're left with just beta naught plus beta 1x epsilon. And then when z is 1, that's the only two values that z can have because it's an indicator or dummy variable. So then this becomes beta 2, and this becomes beta 3x. And so we have beta 1x plus beta 2 plus beta 3 x and beta naught. So we can combine these into the intercept, and then these can be combined. Beta 1 plus beta 3 becomes the slope of x. And this allows us to incorporate the two separate regression equations into one single model and analyze it. And that is the beauty and power of regression. Okay, so that's it for this lecture. Please don't forget to scan your lecture notes by midnight of the date listed on the course calendar. If you have questions, come to virtual office hours. If you can't come to virtual office hours before you need help, then by all means email me, but send me a picture of the question because I may not have that available to me, and a picture of your work so far so I can see how you're approaching the problem. And then I'll be able to help you hopefully very quickly through email. So please take care of yourself and stay safe, and we hope to see you next time.